Hello, so my name's Des Hyam. So thank you all for showing up today and listening to this presentation. A little bit about myself. I'm an applied and computational mathematician, so I enjoy proving things about algorithms. And one of my interests in recent years has been around deep learning, and I think this is going to be a good topic for a general presentation. If I had to pick an overall theme, what we're talking about today is really perturbations. So what happens when you change things, when you move things around? So here's a list of contents of the presentation. I'll begin with a little bit of background about the context of deep learning. And then the first theme we're going to discuss is perhaps a relatively old-fashioned area, but one that's come into prominence recently with the advent of high-performance computing, and that's the issue of floating point arithmetic. So the idea that we don't do things exactly on a computer, we only approximate our computations. Then looking at a slightly higher level question, we want to talk about other types of perturbation. So what happens when things change in the data or in the weights? Those are the kinds of issues that are of interest to me. And that leads us into this idea of adversarial attacks. So this is the case where somebody who's perhaps malicious or criminal is trying to force one of these AI systems to behave in a certain way. So those are types of perturbations which have been chosen very carefully to make things go wrong. I'm not going to go into a lot of mathematical detail. I'll try and keep things as accessible as possible. But for those of you that want to find out a little bit more about the technicalities, I've listed there a couple of recent articles that you can go and have a look at. I'm not going to try to give a precise definition of deep learning or the types of algorithms that are used. We'll just try and think in a slightly higher order manner. But this little picture is intended to illustrate what's going on here. So I'm going to focus on classification problems, and in particular image classification. So we start out on the left-hand side with an image, a set of pixels, so little squares that go together to define the picture. We may well have a red, a green and a blue channel in that picture. And that input image goes into what's essentially a black box. It's a computer program that does some mathematics. It performs operations on all these numbers, combines them together in various ways, and by the time you finish this computation, you come up with an output class. So you've classified the image into one of many potential classes, and in this case, we seem to have decided that this is going to be a dog. Okay, so that's the type of process we're looking at. It takes an input, does something to that input, and outputs a decision or a class. More generally, it may give a probability of this image coming from any out of many different classes. So the picture's taken from this overview. For those of you that want more detail about deep learning, in particular the mathematical side of it, there's lots of good stuff out there these days, but I've given here titles of a couple of expert talks that you can find on YouTube by colleagues of mine, which really put things in a more mathematical context. Now, let's just think about these black boxes. There's lots going on in here, and in particular, these are very heavy computations. And this whole area of deep learning really took off, perhaps for the second time, you might say, around 2012 or so, when a deep learning tool called AlexNet performed exceptionally well in a computational challenge, beating out traditional methodologies. An interesting feature about this was that the program that was written involved training 60 million parameters. And parameters means the weights, the numbers that go into that black box. So these are numbers that you have to choose to make the algorithm work well. So these 60 million different numbers have to be chosen at the same time to make this black box perform the way it should. And by that I mean that when you give it lots of data where you know the answer, it has to give back the right kinds of answers. That turns out to be a huge computational issue, trying to tune 60 million parameters simultaneously. A lot of the ideas that went into this technology have been around for decades, but it was really the advent of high-performance computing that allowed these techniques to become feasible at this kind of scale. I've listed there another couple of fairly recent examples of large deep learning technologies. And again, what I want to emphasize here is number of parameters in these models. So you're having to fit a huge amount of free parameter space once you're training these models. So these are big computational tasks just to get these tools working. And how do we judge these deep learning tools? Well, the ultimate question is, having trained on data that you have around, how will this perform on new data? So if you have this fancy new trained black box and you give it something new, will it get the right answer? That's the ultimate question. That's called generalization. And that's a difficult question to answer, and whether or not you have confidence in the tool really depends on what kind of new data you're going to give to it. So trying to prove things about correctness of this type of technology is tricky and also requires assumptions to be made. It's somewhat obvious that if you train on one type of data, so for example, you have some driverless car technology helping you to see what's out there as you're driving along and identify risks. If you train that classification tool in the summer and then go out in the winter and find that there's snow on the ground, then you can't really expect that tool to deal with that new circumstance if it's never seen snow in the past. So the kinds of results which are proved in a positive way about these tools tend to require assumptions that the new data that you're seeing is in some sense related to or from the same type of population as the data on which you trained. I'm not going to spend much more time on that kind of question. I'm going to look at something a little bit more amenable to analysis. That is sensitivity to perturbations. So if we change the data slightly, what happens to the output? That's a very interesting question. If you change the model slightly, if you've trained those 60 million parameters with using a different training tool and got a slightly different solution, so different weights and biases in the model, will the model still behave the same way? So how sensitive is the model to those numbers that you've fixed in the black box? And it's also of interest to look at the way the computer operates at the deepest level and looking at the errors that arise in floating point operations. So I'm going to look at these three questions briefly, and I'll take them in reverse order. So we'll begin looking at floating point issues. So floating point arithmetic is what we use on a computer. Even people who've used calculators will be aware that you can't store too many digits. There's a limit to how much precision you have in your computations. Most computers these days use IEEE standard computing. So for example, when we multiply two numbers, a times b, on a typical computer, then what we get back from that operation is not just a times b, but a times b with a perturbation. So there's a 1 plus delta factor in the stored answer. So delta equals to 0 would be the exact answer, but we have to accept that there's going to be a small floating point error in that operation. And typical systems will guarantee that delta is not too big. So they'll guarantee that for every operation you perform, the relative error delta is between minus u and plus u for some number u that they specify. This is for multiplication, but the same result holds for other operations, plus, minus, and divide. So loosely speaking, every time you perform a simple numerical operation on a computer, you have to accept the fact that you're committing a slight error in that computation. In many applications, that doesn't matter because these errors are sufficiently small that we can neglect them. And FP64 here is standard double precision, and here's the value of U associated with FP64. So U is 10 to the minus 16. So we're getting 15 or 16 digits accuracy in every computation. I've also listed here the Rmin and the Rmax. So Rmin is the smallest number that you can store in that precision, and Rmax is the largest number. So if you try and compute below Rmin or above Rmax, then that causes problems and you lose accuracy. Now, in recent years, because these deep learning tools require expensive, large-scale computation, there have been moves to make things cheaper at the expense of accuracy. So rather than double precision, FP64, you can move to half precision. And here you're paying the price by having larger potential errors and a smaller range of numbers that you can store. Beyond that, you can go to half precision, FP16, which has an even smaller numerical range. And Google also designed another system they call bfloat16, which is available on many chips, including some Intel chips, which has an even smaller relative error bound with a slightly larger range of numbers that you're allowed to store. So this is really an extreme choice here. Every time you perform an operation, you can only guarantee a relative error of around 4 times 10 to the minus 3. So you're only working to 3 or so digits of accuracy per computation, per elementary operation. And if you think of those deep learning tools with their millions of parameters being used, there's a huge number of floating point operations, adds, multiplies, divides, takeaways going on in those computations. And if we're potentially only working to 3 digits accuracy in each of those, then you can imagine that those errors can build up, and potentially what you compute at the end is nothing like whatever mathematical formula you've written down to describe this computational pipeline. So I think that's an issue. I'm going to talk about a much more modest sub-issue here. So what we did was look at the final layer of a typical deep learning tool, which converts outputs into probabilities by applying a nonlinear function called softmax. And it turns out softmax is very prone to overflow and underflow. So especially with these lower precision units, you can easily run into those errors. And there are alternative ways to write the function, which are mathematically equivalent, but work out differently when you implement them in floating point. And we were able to perform a somewhat old-fashioned traditional rounding error analysis to keep track of the way that errors propagate. And we came up with some results which implied that a shifted version of the softmax implementation should be more accurate than an alternative so-called division-free version. The shifted version is used, for example, in MATLAB and R programming packages, and the division-free alternative is used in scientific Python, and various textbooks promote it. The analysis suggested that the alternative version would be less accurate. What I'm showing here is for some real data, what happens when you sum back together the probabilities that come out, and they should sum up to 1 in exact arithmetic. But if you can see here, for these 2,000 data points, each cross or circle is one answer that we've summed back together. They should equal 1, but this alternative algorithm is losing accuracy, even for this one simple layer in the process. So that's a precise result we were able to show, that this phenomenon does hold. What we're hoping to do in the longer term is get some handle on the full computational pipeline, and what can we prove about the effect of these rounding errors, these floating point errors, in real large-scale computations. And I'll come back at the end if there's time and mention a couple of the ideas that might be useful in that context. Okay. So now I want to move on to more general sensitivity issues. So we're slightly expanding the picture now, taking a step back. And I'm going to give a little example on the classic MNIST dataset. This is very widely used in machine learning circles. It's a very neat set of data that you can play around with, consisting of images of handwritten digits 0 up to 9. So humans have written these digits out. They're labeled, so you know what they're supposed to be, and you can train a network on some of these images and then see how the network performs on some images that you've held out for testing and validation purposes. So these little images are somewhat low resolution, 28 by 28 pixels, so 784 pixels in total on a grayscale. So they're not color, they're grayscale images. And just to illustrate the point I want to make, I trained a fairly standard architecture, which gave 98.9% accuracy. So the trained model, when applied to new images from the data set, was pretty accurate. So this is a reasonably close to the state of the art deep learning tool. And what I want to show here is an illustration of sensitivity. So you may have come across the concept of derivatives, partial derivatives, and they tell you how the output responds to changes. So how does something respond when you make a small change to what's going into it? That's given by the derivative. In this case, we have 10 output components corresponding to the 10 possible digits that you can see. And I've just taken one image here, this digit, which I presume is a 9. And I've stretched out all the pixels into a line here. So here's the 784 pixels. And the height of each point here for a particular output class and a particular pixel is the partial derivative. So putting these together gives us what we call the Jacobian, or the matrix of partial derivatives. But each of these points here, if it's far from 0, if it's very high or very low, means that for that particular pixel and for that particular output class, the output from the model is sensitive to a change in that pixel. And I think this picture makes sense because a 9 is a somewhat curly digit. It looks a little bit like a 0. And in this model, the output class 0 gets excited when it sees changes to this image. So it's intuitively reasonable that the 0 class should be interested in changes that might be making this somewhat more like a 0. Also, the 3 class gets quite excited, and the 8 and the 9 class get excited. So there does seem to be some value here in looking at the partial derivatives of this function, which is doing the classification. That's telling us something about how the output is changing when we make perturbations to the data. Okay, so I hope that's motivating what comes next, which is really the main part of what I wanted to talk about. And this is so-called adversarial attacks. So here is a classic situation where we have an image of a panda, which a sophisticated tool has regarded as being a panda with reasonably high confidence. But if we add 0.007 times this image to it, then here's what we see. And to the human eye, this is really unperturbed. This is really the same thing. So it's still a panda as far as we're concerned, but the sophisticated deep learning tool has regarded this as a gibbon. Okay, so an imperceptible change to the image somehow has caused the deep learning toolbox, the deep learning tool, to give us the wrong classification. This idea goes back at least as far as 2015. This is not a random perturbation. That's the whole point here. This is a very specially chosen perturbation which depends on partial derivatives, in this case of the error function used to train the model. So it turns out that if you make an appropriate small perturbation to an image, there's a good chance that you can cause the classifier to get the wrong answer. So that would be called an adversarial attack. There's an adversary trying to fool the toolbox. There are lots of variations of this idea now. It's become a very hot topic. And in particular, you can print out a physical picture. This is called an adversarial patch. and the person wearing the patch manages to trick the surveillance tool. So this person is regarded as being a human, but this person is not spotted because they're wearing this weird patch, which is specially chosen to fool this automated detection system. Okay, so this is becoming a real war of attrition between attack and defense strategies. People are designing new types of attack and then trying to strengthen their software to make it detect and avoid these kinds of attacks. And it's clearly got massive implications in all sorts of areas. I want to try and finish with by taking a step back and looking at a slightly bigger picture question, which I became aware of when I read this fascinating article looking at inevitability. So is it always true that these systems can be fooled by appropriate perturbations? And these authors use some geometric techniques, isoperimetric inequalities, that relate the surface area to the volume of a sphere in high dimension, to essentially show in some sense that it is inevitable that these attacks can take place. And with a couple of co-authors, we looked at a similar question using a different type of mathematics to show similar results, and also look at other types of perturbations, including perturbing the weights and the biases in the deep learning tool. So I'll just finish briefly just to show you the kind of result that can be established in this area. So this is a tiny bit technical. This is the one bit of maths I felt it was appropriate to put in. Okay, so the first sentence here is really defining what we mean by an adversarial attack. And this is quite a subtle idea, and there's a really neat trick going on here that we're not trying to say whether or not the classification tool is correct. So for a given data point, we have an adversarial example with an epsilon. If you can perturb that data point by an amount no more than epsilon and cause the classification to change. Okay, so epsilon is telling us how much we're allowed to perturb that data point. And if you can perturb it by an amount no more than epsilon and get a new classification, then you've performed an adversarial attack and you have an adversarial example. So we want to know, when can this take place? There are various technical assumptions needed to prove results, which I won't get into, but the key one I wanted to mention was that we're assuming that the data that we're looking at, that is the images, live in what we call the unit radius Euclidean ball in Rn. So n is the number of pixels, and we're measuring distance in the standard Euclidean way in this theory. So here's the kind of result we can prove. I'll just briefly go through it. This is the kind of game that mathematicians like to play. You may have come across similar results depending how much maths you've studied. So there's various assumptions here I'm not going to get into, but there exists a constant k, and you can think of k as being 0.1 in this case. And you're allowed to give me an epsilon as small as you like. So that's going to constrain how much I can make these perturbations. So you can tell me how small my perturbations have to be, and you can make that as small as you like, but you have to give me an epsilon. Once you give me the epsilon, I'm allowed to choose n, which is the size of my data space. It's the number of pixels in the images. And for pictures which have that many pixels in them, a randomly chosen image will admit an epsilon adversarial example. So there'll be one with the perturbation no bigger than the one you asked me for, and I can do that. I'm randomly choosing data points. That will happen with probability at least k. So at least 10% of the time this will succeed. Okay, so that's a negative result, saying that any classification tool in sufficiently high dimension must admit these adversarial examples. They must be around under these assumptions. Now, the original work I mentioned required the size of the dimension to scale like 1 over epsilon, and 1 over epsilon squared, and the version that we proved improved that to 1 over epsilon. So you don't need to take a huge dimension in order to deal with small perturbations. So under these assumptions, adversarial attacks are pretty likely to exist. So you can make these perturbations in general. Okay. So just to finish off, there are all sorts of interesting follow-ons from this kind of work, and lots of questions that you can think of. First of all, that result I just gave was about existence, and from a mathematical sense, it's a classic example of a non-constructive result. We don't tell you how to construct the attack, we just tell you that one does exist. So it's not clear that these can be computed. So maybe things are not as bad as they seem. You might not be able to find these perturbations if you're the attacker. Another interesting question is how to measure perturbations. We're using what's called the Euclidean norm in that work, which is the standard way of measuring distance between things. But once you get into high dimensions, it really does matter how you measure size. And depending on whether you want to perturb every pixel, just one pixel, how you want to quantify the effect of perturbing many pixels, do you square them and add them? Do you take the biggest? Do you take some other power of them? There's all sorts of ways you might want to decide on measuring size of perturbations, and they will certainly affect these results. An even more interesting question to me is what is the true dimension of the data space? You know, we may have millions and millions of pixels in the image, but it might be that all the images appearing in nature can be described in a much lower dimensional setting. So we'd refer to that as a manifold in mathematics. So maybe the space of actual images appearing in nature is much lower dimension than we might think. So we really are working in lower dimension and therefore less susceptible to these types of perturbation. And another issue which I hinted at earlier is simply the variety of different types of attack that are out there. You can think of perturbing the input, but you could also perturb the numbers inside the black box, some of the weights and biases. You could change the architecture slightly. And more generally, you can do things like add neurons and see what the effect of that might be. Can you secretly add a neuron which doesn't affect the performance on the training set, but on the validation set, but does somehow affect the performance on one particular data point of interest to you? So there are all sorts of sneaky tricks that you can think of analyzing. Are they feasible and can they be defended against? Okay, so those are all somewhat negative things to talk about. On the positive side, we can think of algorithms that identify attacks and therefore try to reduce their effect. We could also compute what we call saliency bounds. So maybe I tell you that picture is a gibbon, and I can also guarantee that if you don't perturb it by more than 10 to the minus 2, it will still be classified as a gibbon. So maybe we can put some bound saying that within this region of the image that you gave me, the classification tool will still give you the same answer. That might give you some more confidence in the output. And then returning to this floating point issue, there's some really interesting work coming out about stochastic rounding. So this is a different way of performing arithmetic, which has some randomization built into it. So rather than rounding to the nearest floating point number, you stochastically round to the highest or lowest nearest floating point number. That has some really neat properties. In some cases, you can show that on average, this will give you the right answer, for example. So you can get some sort of statistical result from this. And finally, just let me say, I focused here on technical issues of interest to me, but of course, a lot of this stuff does have implications and needs to be considered in a much wider context. So there's lots of opportunities in this kind of world for collaboration, discussing what these things mean, how they should be dealt with, whether they're important, and so on. And finally, yesterday I advertised a postdoc in this position. So if there are any early career researchers who are interested in these areas, then please feel free to get in touch with me. Okay, thanks. I think I'll finish at that point.